Now that we have Newton's second law in the bag, it's time to see what we can do with it. And to really work with it, we need to understand the concept of free body force diagrams, because it will tell you what's happening to the object. Namely, it's identifying all the forces acting on the object. So we're going to do this and show how we can solve a problem. And let's start with, say, a block sliding on a surface at speed v. Now, the contact force can be divided into two components. What's in contact with the surface? Well, the block is. And if it's sliding, there's two pieces to this. We have the normal force. Normal force means a force perpendicular. Perpendicular to what? Perpendicular to the surface. So it's always perpendicular. We can draw it in like this. Arrow pointing up, normal. And then also we have the friction force. Well, you probably can understand that if it's moving this way, the friction acts the other way. Now, it's generally true in most problems that the friction force is acting opposite to the motion. It doesn't necessarily do that. You could have it going in the same direction. For most problems, it's working opposite. Let me put it this way. If a surface is stationary and an object is sliding on it, then the force is in the opposite direction of the motion. Okay. So here it is, friction. And then we also have gravity, good old gravity, which pulls straight down on objects generally, at least I should say, toward the center of the earth. We're talking about Earth, which we usually are, and that completes the forces acting on that object. Okay, now let's do an example. We got 100 Newton force applied to a 10 kilogram block on a surface with 30 newtons of friction. Let's determine the acceleration. We draw the free body, 10 kilogram block. We'll divide this into the x and y components. Okay, so the applied force is 100. That's given. Then we have a 30 Newton friction force. Let's put that in. We have weight, gravity tugging down on it, and that's equal to mg. That's an equation, mass times gravitational acceleration. And finally, the normal force, which points normal to the surface. So there it is, all forces identified, and I'm going to stick acceleration on the diagram, but I'm not going to stick this vector onto the block because it's not a force. It is what's happening to the motion, but it's useful to have on there. Visually, you can see that this force wins. It's bigger than this force opposing it, so it accelerates to the right. Well, what's the sum of the forces in the y direction? By inspection of the object, if you watch it for a while and recognize it's not accelerating in that direction, we know it's zero. No acceleration, no net force. And observing the sides of these vectors, if I drew them well, then they'll be the same size in opposite directions. Well, the sum of the forces is always ma, it's the net force, and in this case, it's zero in the y direction. What does that tell us? We can take this force minus this force and equate it to zero. Normal minus mg equals zero. Therefore, it holds that the normal is equal to mg. Now, this is a useful idea. Normal equal mg. It won't always be true, but in a simple situation, block on a flat surface, that's it. Okay. Now the more interesting part about what's happening in the x direction. Sum of the forces in the x direction is ma. We know that. That's like the big picture. Now let's ferret out the little details. What are those forces in the x direction? Well, the answer is we got the applied and we got friction. So let's subtract them. This one, basically you do this. It kind of follows common sense. The big one minus the little one will give you the size of the force in the direction of the net force. And that's ma. The net force is ma. So really, we just wrote the equation. There it is. So what are we trying to find? The acceleration. Let's solve for it. Fa minus f over m. There's the numbers. 100 minus 30 over 10. Voila, 7 meters per second squared. And we just solved the problem with the assistance, the greater understanding of the details of the situation that was manifested by the forces on the block, namely the free body force diagram. Let's do another example that's actually quite similar to the one we just did. We're given the acceleration of the block is 2 meters per second. We're also given that the friction, which I just drew on there, is 6/10 of the normal force. Then what must the applied force be? We know we have to have an applied force greater than the friction for there to be an acceleration. So that's not too hard. Let's put it all together. Here's gravity acting, and it's 5 times 9.8, which is 49 newtons. And then we have the normal force, since we just learned that it's equal and opposite to the weight. Because there's no vertical acceleration, we know it's 49 newtons. The acceleration is 2 meters per second is given, so it must have an applied force of something. We're going to figure that out. So sum of the forces in the x, we know the sum of the forces in the y is 0. And this is ma. So what are the components? Well, it's the applied and the friction opposing it. So Fa minus F is ma. So let's solve for Fa. It's just ma plus F. And m times a given, and friction is 0.6 times 49, 0.6 times the normal, and out pops the answer. That was pretty easy, wasn't it? Something I want you to be aware of is when we say ma, sum of F is ma. Well, that's inherent in the way I just said that. The sum of F is ma. Ma itself is not an actual force, but it's the acceleration of the mass. That's the result of all the forces on the mass. So in other words, when I say ma, F equals ma, you can equate ma to these forces. Maybe it's just one force. Maybe just gravity alone is acting on it. So gravitational tug, that force is ma. You still have to say ma is not a force. Ma is a description of the sum of the forces. In and of itself, there's no particular force identified in this part. The identification of all the forces to produce this is given on the left-hand side, where we break down all the forces, like we did here, Fa minus F. Those are actual identifiable forces. The applied, the friction, the ma is the result, not a force. Make sense? All right, now we're going to take free body force diagrams a step further to inclined planes, which we will do in more detail soon. But just to kind of get warmed up to it, here's a inclined plane and a block on it, angle phi. We accelerate down. Surprised? No, you're not. So we have weight acting straight down. Fg is equal to mg. Now, remember how we said that the normal force, like what we had up on this one, the normal force was equal and opposite to the weight. I wonder if it is now. Is the normal force straight up like this? Well, no, because by definition, normal is perpendicular. So actually, it looks like this. Moreover, you'll notice that the length of the arrow is less. Now, it may be intuitive to you that this normal force gets less as the angle gets steeper. If it's not, think about making this angle 90 degrees. So if this ramp was vertical and you put the block on here, there'd be no normal force at all. So it turns out that any angle is going to reduce the normal force a little bit. If you don't understand that, ask me to explain it better in class, okay? Well, now, the normal force is less than the weight. That's always going to be true in this kind of situation. Now we also have the part that's of gravity that's trying to accelerate it down the ramp. I'm going to call that F parallel. Parallel to what? Parallel to the ramp. So that's part of the weight. We also have another part of the weight, namely the perpendicular component. So I'm going to call that F perpendicular. This force, along with the parallel part, effectively replaces this gravity. Gravity can be broken up into those two components, as they're called. And finally, we have the friction. Friction is opposing it. and it's in the opposite direction of the motion, which is presuming right now to be down the ramp. We are presuming that. So that's how you set this scenario up. And what we need to do at this point is we got this friction in here, but I wonder how it's affected by the fact that we put it on this ramp. You could probably guess that it is affected, and you'd be right. So let's now take a step back, so to speak, and look at some of the characteristics of friction in different situations.